Good morning, everyone, and welcome back to today's class of 3201. So last week we were discussing the basic feature types, whether how many feature types are there in GIS for both raster and vector. And then we realized that there are four feature types, and don't mix it up with data types. So data types and feature types, these two are different. So data types is how many types of data are there. Okay, so for example, you have a data, and what are their types? Do you have for example, just from the perspective of statistics, do you have descriptive data, or do you have categorical data, something like that, nominal data? All these things are data types. And the feature types, on the other hand, are how are you representing. For example, you can represent a house using a point. So at that moment, that point is a feature. That means whatever that is in your map, or if something is an element of your map, that one is a feature. It could be a boundary of a district. It could be a location of some feature. So see, I said a location of some feature. So in this case, the feature could be the academic building of BUP, or MPAs of BUP, or the entire BUP could be a feature. Okay? So if you are mapping the entire country, and then if you want to map out all the location of the universities, so at that moment, you will represent BUP using just a single point. Okay, so that's a point feature, or we could say that's a punctual feature, because that's a point. All right. If the map is not vector but raster, at that point there would be just a single cell. Okay, so just like BUP, Dhaka University would be getting represented just a single cell. Since you are talking about a larger scale, you are talking about that you want to map out all the universities in Bangladesh. So you are considering a large area. You are considering the entire area of Bangladesh. And in compared to the entire size of Bangladesh, the size of BUP or Dhaka University are very, very small. Okay. So, and then you say, all right, so now I want to map out all the road networks of Bangladesh. Okay, so at that point, the road networks, they are getting represented as lineal features. So that means all the road networks are getting represented as lines. Okay, so for example, if this one is a road in reality, and then the moment you map it out, you will be calling this as feature. So this feature is a road. That's how we say. Okay, so that we see an element and we say, okay, this feature is a road, and then we see one element and we say, okay, so this feature is BUP, or BUP is getting represented by this point feature, or excuse me, by this point or by this feature. So the element of the map is feature. Okay, it's not data. And that's what we discussed, the different types of the features. Or in a more simplistic way, how many dimensions do we have to represent entities of reality in maps? So we had punctual, that is 0-dimensional. We had linear, 1-dimensional. And then we talked about aerial, which is 2-dimensional, and then surficial, which is, although in many GIS, they would identify these features as 3-dimensional, but actually they are 2.5-dimensional because they are superficial. They are talking about only surface. Very soon we will talk about this in a little bit more detail. So the resolution of raster data affects some of the things, And these things are the classification, also the area or the perimeter or the boundary, and the accuracy, and so on. Okay, so how the classification is getting affected, and what is classification? So for example, you have one satellite data and you want to find out that, okay, so this satellite data is just data, right? Just like the image that you see in Google Earth, or if you access Google Map and if you turn on the satellite view, you see houses, you see vegetations, you see lands, roads, and water bodies. But then there are also so many things in between. There are some bare land, there are some agricultural land, there are people moving, there are cars running. So too complex. All right, the entire image is a little bit of, there are so many things. It's a mix of multiple things, but we do not want to have all these extra elements or all these complex elements. We want a simplistic view for our analysis. So what do? We make classifications. Okay, we divide the entire image into different classes. And how do we do that? Well, we can do it based on the land cover, or we can do it based on land use or something else. Okay, that could be, there could be multiple perspectives that we can utilize. Now, when I do that, for example, if we're doing the classification based on land cover, then what do we say? Whenever we say vegetation, for example, we have 4 classes. One is vegetation, one is water, another one is urban, and finally we have others, that is which are not urban, nor water bodies, nor vegetation. All these elements of the image will be categorized as others. So we see vegetation, and then we identify that, okay, this is vegetation. We see urban area, we say, okay, this is urban area, we identify that, and the water bodies as well. And all the other elements, we also identify them as others. Then we run some algorithm, we run some processes in our computers. Okay, and automatically all these vegetations, urban areas, water bodies, and other classes, they get created, they get classified, the image gets classified. Okay, so at the very first moment when you see an image, do I have any image here? For example, this one, so it doesn't have any class. We see just pictures of some green area, then pictures of some purple pixels, and that's it, and some dark pixels. Okay, so if we look into the attributes, there is nothing, there is no classes, there is no information about the features, okay, or the entities of the reality. So at that moment, but what we do is we say, okay, this is vegetation. We tell the software that this is vegetation, this is urban area, this is water bodies, and then automatically, by running the algorithm, it creates these classifications, and finally we have these sort of maps. All right. So in these maps, it says that, okay, so this is vegetation, this is urban area, and this is water bodies. So it maps out in pixel, in raster form. So in raster form, when it creates this raster form, I mean, what happens is there are some details of reality is lost. How? Because we know that raster has grid, but in reality, it's actually not grid. It follows its natural boundaries. So that's why that could be man-made as well. So all these boundaries, they could have their fine details. They could have their fine boundaries. Okay. On the other hand, in raster, everything is cell. So if the cell, the size of the cell is increased, then we might lose some details. Okay, we might lose some details. So if we lose some details, that means our accuracy is also being lost. So we are losing few things. We are losing both accuracy and we are also losing precision in this area. And then also we are losing some of the areas. How? And somewhere the areas are increasing as well. For example, if you would like to map this one out, and then in your raster, if the pixels are very small, then you are having this size, for example. Okay, so this is getting represented as urban area or this class. And then if you look into the next raster, then you will realize that the area has increased. For example, this entire pixel now became the urban area. So these pixels, which were water bodies in the previous example, in this example, now they have transformed into urban area. And now, if you now reduce the resolution, spatial resolution, that means you have increased the size of the cell. Now we suddenly realize that, okay, so this pixel is completely gone. Okay, it's lost. Why? Because of the dominance of water body pixels. So now this pixel, which covers this much area, it realizes that 75% of the entire area is covered by water. Okay, 75% of the area is actually water bodies, and 25% is urban area. So what it does is the algorithm says, okay, so in my pixel, 75% is water bodies. So this entire pixel will be represented as water bodies because one single cell or pixel can hold only one single value or only one class. So it discards these land cover or urban area and then convert the entire pixel, okay, or all this region as water bodies. So sometimes the area is gained and then sometimes the area is lost. So now if you look into this pixel, you might say that, okay, so my area has been decreased because this is just 1/4 of the image. On the other hand, if you look into this fine grid, you might say that, okay, I have somewhat to the same area as the reality. But then if you look into this medium grid, you might say that, okay, I have increased or I have gained some of the areas. Okay, something like that. Anyway, same is for this vegetation pixel as well. Look, we have here, so we have some gain in this medium grid, and then we have we completely lost 2 pixels, okay, in this grid. Although by comparing these two images, you might say that, all right, we didn't really lose any information or any area because this pixel has now getting replaced by this pixel. So that's how the change of resolution affects all these areas. And change of resolution also affects classification. I think I gave an example previously, or didn't I? I'm not sure. Okay, so few years back, do remind me if I have already mentioned of this example in past. So a few years back, there was suddenly a buzz on the newspaper saying that Bangladesh has lost a significant amount of forest in Sundarbans. Okay, there was a research article published, and it was saying that Bangladesh has lost a significant amount of forest areas. So Bangladesh Forest Department was in under pressure. Excuse me, because the national media were reporting that, okay, you guys have lost a significant amount of forest area in Sundarban, so what are you doing? Then BFD was saying that, okay, we didn't lose that much, but no one was listening because people like to hear the complaint. All right. So, and the gossip. So what happened actually? So what happened was there were, by now, from 3205, you have already introduced to remote sensing a little bit. You have been introduced to the spatial resolution. And in early warning and forecasting, I think in that course, you were introduced to the satellites. So what happened was, before 2015, there were no Sentinel. So Sentinel was launched in 2015 and started giving data from 2016. And before that, we had freely available data from Landsat. And the resolution of Landsat is 30 meters, right? So that's 30 meters, and that is Landsat. And Sentinel has resolution of 10 meters. So that's Sentinel-2. So now, for example, this is Landsat. This one is Landsat. So LS, Landsat, and this is Sentinel-2. Okay. So what happened is, for example, so Sentinel-2 means 10 meter means 10 meters by 10 meters equal to 100 square meter, right? So that is Sentinel-2. And if you think of Landsat, it's 30 meters. So 30 times 30 is 900 square meter. Now, do you realize the difference between the area? Although it seems, okay, 30 and 10, not much of difference, only 20 meters difference, that is 1/3. But when you come to the area, it's not really you cannot really say it's 1/3, okay, because that's 100 square meter and then 900 square meter. Okay. Excuse me. So, and in fact, if I draw this, you will realize it more. So 30 meters. So it's dividing this 3 and 3. Okay. So if this entire pixel is of Landsat, then this small pixel is Sentinel. Okay, because this is 10 meters, 10 meters, 10 meters, in total 30 meters. And then we have 10 meters, 10 meters, 10 meters. That is 30 meters. So this is actually 1/9 of entire Landsat pixel. So now, for example, at some point of time in 1990 or in 2000, let's say 2000, or okay, let's say 2005. So 2005 or 2006, you had 1 pixel of Landsat, which is vegetation. Okay, and so in reality, the area, I'll change the color. So in reality, the area of the vegetation was like this. Okay, so this is vegetation. This is vegetation part, and this is something else, water bodies or sea or something else. So you had this vegetation, and that's why in 2006, from Landsat, you have received that this entire pixel is vegetation. Why? Because you see these lines. So most of the area, let's say 60% of the area is covered with vegetation, or 55% of the pixel is covering a vegetated area. So that's why this pixel was classified as vegetation. And then in 2016, when the Sentinel data were available, now a group of researcher or a single researcher come in. He wants to, or she wants to, or they want to understand the boundary of Sundarbans from these Sentinel data. So remember, Sentinel data is how much of spatial resolution? 10 meters. So that means now we have this is Sentinel data. Okay, it's not a fine drawing, but you understand. So these are the sentinel pixels, if they are perfectly aligning with the Landsat. So now, over the time, within these 11 years, we have lost a little bit of vegetation. Okay, we have lost a little bit of vegetation, and our new vegetation boundary lies like this. Okay, so this is our vegetation. Now what happens is you say, okay, so since this is our vegetation, in sentinel pixels, the vegetations are only these pixels. Okay, so you see, if you were thinking of previously, then you might say that, okay, I have these areas. So I will identify which were the deforestation using red. So these pixels are actually lost due to deforestation. Okay, so you have actually lost 300 square meter of forested area. That means deforestation only happened in 300 square meter. Okay, from Sentinel perspective and comparing with the reality. All right, but if you compare with Landsat image, then you have lost a forested area of 1, 2, 3, 4, 5, 6. So in reality, you have lost 300 square meter, but according to the by comparing to the Landsat, you have actually lost 1, 2, 3, 4, 5, 6. So 600 square meter. Okay. So now this is just a single pixel. This is just I'm only talking about, for example, 900 square meter. Okay, since this is a single pixel, so this is 1 pixel. So I'm only talking about this 900 square meter scenario. So in 900 square meter scenario, it says that you have lost 600 square meter. So now compare it with multiple, which is the twice of the lost, the actual lost. Okay, so that's 2 times higher than the actual lost. So if it's 2 times higher than actual lost, now compare it with multiple pixels. Let's say compare it with 100 pixels. Okay, so if it's 100, then your lost will be 6,000 or 60,000. So 100 is 60,000. 60,000 square meter. Okay, so it's a, now you are saying that which is in reality, which is 30,000 square meters. Okay, so now you understand that because of this report, in reality, Sundarban didn't really lose that much area, but then since the researcher didn't consider the differences between the spatial resolution, that is the grid resolution of the data, now they are reporting falsely that, okay, you have lost a significant amount of the forest. Okay, so that's how the changing of resolution affects the classification and the studies as well. Okay, so advantages. There are a few advantages. Since it's a matrix of cells, it's really a simple data structure. Okay, there is nothing complex. There is no differences between cell to cell other than the values. So from one cell to another cell, only the values are changing. Okay, the structure of the cells, they are not changing. On the other hand, if you look into vector, then you have point, line, polygons. So the elements, the methods that you draw, that means the features, they are also changing. Okay, so feature types are changing. If you want to make a punctual feature, so you have to rely on the point. If you want to draw a linear feature, you have to rely on the lines. If you want to represent an area, you have to rely on the polygons. Okay. On the other hand, in raster, what you do is for this punctual, you represent it with one single cell. That's punctual. And if it's lineal, you represent it with a series of cells. So that's linear. If it's area, then you represent it with a cluster of cells. That's area. Okay. And if it's surficial, again, you represent it with a cluster of cells. That's surficial. Okay. So it's just cells. The primary elements are the cells, and cells are what building everything in raster. So it's very it's more simple than vector data types. Okay, and sometimes, however, sometimes raster data could have attribute table as well. Previously, I said that in our previous example, we didn't see any attribute table, but time to time, a raster data could also have an attribute table. Also, you could create one attribute table for your raster data, or the data that you have, you can transfer it to, from the cell, you can transfer it to an attribute table because you want to export the attributes or the values of the cell. You can do that. So because of this simple data structure and because of another properties of it, and that is it spreads throughout the area. Okay. So what do I mean by that spreads throughout the area? In vector, if you draw a line and that line only exists on the location of that line, it does not exist in the surrounding areas. But in raster data, if you draw a line, this is the entire pixel things. So you have drawn a line with these pixels. So still in surroundings, you have these multiple pixels and they have values. Okay, and because of that, it's very easy to perform spatial analysis. Okay, because now you can do simply, you can do maths. You can say, okay, so plus this one plus another layer. I'll find out what that is. Okay, you can also do multiple statistical analysis using the same formula, because in the statistical analysis, you have to, you know, add them, multiply them, divide them in a series of order. However, just like as we talked about in previous class, now if you have one line and then you have another line, now if you want to add them or multiply them, how can you do that? It's not really possible, right? You can join them, you can connect them, you can draw one over another. That is possible, but that's drawing, that is not analysis. Okay, but how can you multiply two lines? Because these lines, they do not have any value. On the other hand, the raster pixels or cells, they have values, so they can be multiplied. These values can be multiplied. So then the surface analysis can also be done, okay, because they represent a continuous surface, that is DEM, for example. Let me show you the DEM, wall DEM very quickly. So do you see my QGIS? Yes, no?
Yes, sir.
Okay, and guess what is this location?
So this is Indian subcontinent.
Okay, and what this is?
So this is Bangladesh.
Bangladesh, right? So Bangladesh, do you realize that Bangladesh is pure completely black?
Yes, sir.
Right? Why? Because well, let me find out. Because you see, what happens is the elevation of Bangladesh is very low. Okay. So since the elevation of Bangladesh is very low, it's when I'm trying to map it with two colors. So here I mapped with a minimum elevation and maximum elevation. So I identified the red band or red color as the maximum values, and the minimum values are the green values. Okay, so I said that, okay, and then I mapped it out. And in these maps, you realize, for example, in this region, the Sylhet and Tirikong hill tracts, and a little bit of Mymensingh has hills, so that's why they have higher altitude. So since we are also considering the Himalayas, so we have these lines, okay, which are red, right, and which are very, very red. They are the tall mountains. So Himalayas, and we have a little bit of in the South America, okay, and also a little bit in Europe. Where is Europe? Yeah, so a little bit in Europe as well. So that's elevation. And since this is elevation, so this is the surface, right? It's a surface. It's the height of the land, or the height of the landform in this region. Let's say if I can change the history. No, this is best. So now, using this surface data, what you can do is, for example, now if you delete all these regions, okay, or if you'd like to just keep, sorry, if you'd like to just keep this region, now you can do surface analysis from this region, from this a little bit of Himalayas and Indian subcontinent and Bangladesh, and you can do surface analysis, and you can understand that how rivers are flowing from Himalayas to the through the India and through Bangladesh, and then they are going to the Bay of Bengal, all right? How are they behaving? And also, if you want to do a study on flood, you can study the surface, and you can understand how the flash floods are happening in our country, how the waters are actually moving towards our country, okay? How they are moving towards the lower catchment. And so that's how we do surface analysis. That is what I mean by this surface analysis. You analyze the surface and you find out what's going on. So I have already discussed about this point, the ability to uniformly store point, line, polygons, and surface. So it was explained in this in here. So by using points, you are representing point. By using series of cells, you are representing linear feature. By using cluster, you are using aerial, again cluster, superficial, and this one is also cluster. Okay, so there are the cluster of pixels. So if I turn them off, for example, we're seeing multiple colors. So I'm saying, sorry. Okay, let's try hill shade. Let's see what happens. Now you will understand it even more. Okay, so sorry, where is my hand? So now the landform is even more clear, right? Now the Bangladesh is visible by applying the hill shade effect. Okay, so from this hill shade effect, now you can study. So this is the resolution is a little bit coarse. Okay, it's not that high. So from this hill shade, now you realize that, okay, so these are the areas which has low elevation. So whenever it rains in this region, and in this region the water comes into these areas and the river flows, and you see these are elevated areas, and through all these elevated areas, for example, imagine this one as one dam or one wall, okay, a continuous wall or a dam, and in this dam you have only one single gate. That's Bangladesh. You realize that's Bangladesh. Let me zoom out. So see, here you go. One continuous wall, another continuous wall, and the rainfall are falling all these regions. They are going through this channel, and this channel has only one gate or one way to release all the water bodies into the sea, and that's Bangladesh. We have another one here, but then for all this region, we have only one single point, and that's why flood is very interesting. Flood is a yearly phenomena for us, and it's a very interesting phenomenon to study. Okay, anyway, let's try to change it to not hillshade but single band gray. Bye. So now you see that, okay, so these are all single, all of them are pixels, okay, getting represented into just a grayscale in black and white. So higher elevations are white and low elevations are black. Even in the seas, they also have pixels. So if I zoom out, you have this entire collection of pixels. This is the raster image. And in this raster image, you have for every location, you have pixels. So we have the resolution, we have height of 7,358 meters and minus 400 some pixel values. So if I zoom into this native resolution, so, and if you further zoom in, then you have these pixels. Okay, these are the pixels. So now we can, what you can do is you can not square meter. I don't want to calculate meters. Okay, let's do meters, right? So if I zoom in and if I say so 1 pixel is almost 152 square kilometer or 100 square kilometer. Okay, so 100 kilometers by 100 kilometers. That's the resolution of spatial resolution of this image. Oops. Anyway, so let's get back to our lecture. And the ability to perform fast overlays with complex datasets. And that's very true. It overlays very fast with the complex dataset, because if the dataset is complex, if it has complex heterogeneous values in the cells, at the end of the day, what it has is it has only the cells. Okay. So for example, you have a very detailed road network of Bangladesh. So when I say very detailed, you have these small paths. I mean, আমরা বলি না যে মাটির রাস্তা. Okay, you have these small paths as well mapped out in this road network. So it's a very complex now. It's a very complex, and it has very much detail stored in this data, in the vector data, not the raster data. Okay, so if you want to map it out, it's going to take a while to load, because it will need to map out every single vector lines that it has created. On the other hand, if you map it with cells, then, I mean, if it's vector, then it has all these lines and lines going on and lines going on. So it needs to map out every single element, right? But if you use it using raster, then it needs only to map out these cells. It doesn't really matter what's inside, what's the value of these cells. It only matters that it only map out the cell. It only need to map out the cells. Okay, so you might have very complex values. You might have heterogeneous values stored in these cells. For example, in these 9 cells, you have 9 different values. Okay, so these 9 different values will not affect the loading of this layer. Okay, because at the end of the day, you are loading only the 9 cells. It doesn't really matter what's inside them. Okay, it only matters how big they are or how small they are. So limitations, well, from this previous example, you have already realized one of the big limitations is the accuracy. So in many times, the accuracies are lost, okay, because of the structure of the cells or the size of the cells. And also, in vector, for one line, you have just a single line, but in raster, for one line, you have a series of cells. So since you have series of cells, for example, this is the line. So since you have series of cells, that means in computer memory, they need more space to store their data. So that's why raster datasets are quite large datasets. Okay, so for storing the same amount of vector data or the features, for example, road network, even river network, if you might need few kilobytes to store river network of entire Bangladesh, whereas it might go few megabytes or few hundred megabytes for storing the same river network in raster form. And then there is also loss of precision. Okay, that is involved when you want to convert the raster back to the vector. So you, for example, I will give you one quick example. For example, you want to study the river networks. Okay, you want to do spatial analysis. You want to do that how over the time the river networks has changed. So what you do is you take one river network, for example. So that's 2 lines. Okay, and then you take them in pixel in raster, and in raster they would look like maybe something like this. So this is your river. So that's your river, right? So your river has this boundary now in raster format. So when it was in vector, it looked like this. Now in raster you have this, and what you want to do is you finished your studies, you are done with your spatial analysis. Now you need to convert it back to the vector. I mean, you want to see it, how does it look like, other than seeing it in cells. So if you convert it, and if you give a command that smooth the lines, I mean, instead of having all these blocky lines, smooth it out. So it's going to smooth out like something like this. Okay, because it needs to go through, it needs to contain all these pixels. Okay, so that's why it draw a line like this, which in reality it's not like that. And why is it happening? Because the size of the pixels are too large when you created them. Maybe you have created them as 30 meters by 30 meters, or maybe you have created them as 10 meters by 10 meters. Okay. On the other hand, in vector, they were at the possible level of precision. So some precision are getting lost, some accuracies are also getting lost as well. So that's lecture. And we will go through next one for a little bit. Do you have any question for now? Okay. So now we are talking about vector. We will talk about vector, but before I go back to the vector, I would like to point out this one. The difference between 2.5D in GIS and the difference between three-dimensional. So on the map on the top right corner, you see a superficial map. Okay, so that's a DEM, and here are the hills. Okay, maybe some trees on top of it as well. So it might be not DEM, it might be DTM. Okay, sorry, DSM. So what's DSM? Don't forget this. So DSM are there are DSM, DTM, and DEM. So D stands for digital, M stands for model. Okay, so S is surface, digital surface model, T is terrain, and E is elevation. Okay, so digital surface model, digital terrain model, digital elevation model. So what are the differences between them, or what's the difference between them? Well, for the surface, it considers the surface. So whatever that is, it doesn't matter. Maybe on the surface there is a boat, maybe on the surface there is a house, maybe on the surface there are trees. So it will take only the surface of everything. So just like it says, the surface of everything. So that means if you have trees on the ground, the height or the surface of the trees will be recorded in this model. For example, if these are trees, then this is a DSM, okay, because the trees are recorded as well. But if these are hills, and if these are hills, and on this land, they have, for example, excuse me, they have houses built, but the houses are not recorded, or they have trees, but the trees are not recorded. Only the ground surface is recorded. That is, so when we say only the ground surface, we usually say that's a terrain, right? So if only the natural surface, that is the ground surface, is recorded, although that surface has trees on it and houses or other structures on it. However, if the model only considers the surface of the ground, then we say it's a DTM, digital terrain model. Okay, and digital elevation model is somewhat a mix-up. Okay, it could be a surface of the ground. At the same time, it could contain some surface from treetop, that is the canopy cover, or it could contain some surface from houses or other structures as well. However, it tries to get to as close as to DTM as much as possible. Okay, it tries, but it cannot. Okay, it contains some of these surfaces. So that's why when you want to do surface analysis, you should rely on DTM. Okay, especially if it's something like flood or something like that. You should try to avoid DEM or DSM. Being said that, it's hard to get DTM from satellite data. Okay, excuse me. It's hard to get DTM from satellite data, and all we get, there are some satellites, for example, from US we have SRTM, okay, and from Japan we have ASTAR. So ASTAR is from JAXA, and SRTM is from, I think it's from NASA or some sort. I'm not really quite sure. So you can get them from USGS as well. So USGS has one portal. So USGS, sorry, United States Geological Survey. So these two gives out DEM data. Okay. Now, if you have map of forest, and if you have map of and the height map of forest, and if you have height map of the buildings, so for last 2 years, I have been talking about we should map out the building heights of Dhaka and other things. And the reason behind it is when we have these building heights mapped out of the entire city, then it would be very easy for us to do it, for us to study waterlogging and flood inside our Dhaka city. As long as we have this building information, the elevation data that we have are in some way they are useless, because this elevation data has some errors due to the buildings. Okay, they cannot really truly represent the DTM. But once we have this DEM and once we have these building heights, we can eliminate the building heights or the buildings from this DEM, and we can now utilize DEM, and we can find out how the landform looks like, and how the waterlogging is happening when it rains a little bit. So yes, so these, all of them, they are superficial data and they represent surface. So I will point out quickly, if you look in this place, you will realize that it went like this. Okay, why? Because it's only representing the surface. In fact, if you look into this region now, okay, same thing is happening. Okay, it's going some sort like this, if you think of this boundary. So I'll draw it out for you. So it's going to, oops, it's going like this. So you see all these hills or trees or whatever that is, they are actually hollow. There is nothing behind this surface. So that is 2.5D. On the other hand, if you think of this block, then this is, you have multiple blocks. I mean, when we were a kid, we played with these sort of blocks, green, red, and something, and we tried to build things. So if these are bricks or these are blocks, if you put one top of another, then this is 3D, that is 3-dimensional, because that's a solid model. On the other hand, and at the bottom, if you look into these images, then you have this marble stack on each other. So this is a solid model as well. Why is it a solid model? Because if I try to identify the height at the middle, then I have one height here. I have multiple height throughout this marble. Then I go to the next marble. Next marble starts here. I have multiple height to this marble. And then I go to the next marble. I have multiple heights to that marble. I go to the next marble. It has multiple heights to that marble. I go to the next marble, and then it has multiple heights. And that's the ground. Okay, so I have 1, 2, 3, 4, 5 marbles, for example, and every marble has their they are solid, so they have multiple heights. That means height can be measured at any point of time. But if I want to measure height at some point here, for example, this one, so I have only height of this region. I have only height of this point, and rest is hollow. For example, if I want to measure height here, then I have height at this point, and the rest is hollow. Okay, so I think now you understand what's 2.5D and 3D. Just look at this and go through this slide and Google it a little bit, and you will be more clear about the idea.
Sir,
yes.
Sir, আগের পিকচারটা, আগের স্লাইডটাতে স্যার এই মার্বেল গুলার জায়গায় আমি যদি টেনিস বল দিয়ে এরকম স্ট্যাক করতাম, টেনিস বলের তো ভিতরে ফাঁপা, তো সেটা ইভেনলি 2.5D, কিন্তু এভাবে করলে তো একটা সলিড ফিগারই আসতেছে, তাহলে কি হবে এখানে?
না, টেনিস বলও যদি হয়, টেনিস বলের ক্ষেত্রে আমি যে পয়েন্টটা বলতে চাচ্ছিলাম সেটা হচ্ছে in this surface, if you want to take height, you can take height only at one single point because that's a surface. So তুমি এইভাবে হাইট মাপতে চাচ্ছ, ফর এক্সাম্পল এটা হচ্ছে তোমার, আমরা হাইট মাপি না আমাদের, তো এটা হচ্ছে ওই স্কেলটা, and the surface goes like this. Okay, cross sectional বোঝো তো, একটা সারফেসকে তুমি ক্রস সেকশন করছো, so ওই সময় তুমি যদি হাইট মাপো, so you are able to measure height only at a single point, and that's this point. Okay, this is the point where you can measure the height. On the other hand, if these, so if you can measure only one single height at a single point, that means that's a surface. Okay, because it's hollow at the bottom, it doesn't have anything. Now if you stack, instead of marbles, if you stack tennis balls, let's say we have 3 tennis balls, then you can measure height at this point, at this point, at this point, at this point. So we have 1 2 3 4. So this is not superficial anymore. Okay, এবার কি ক্লিয়ার হলো? যদিও টেনিস বলগুলো ফাঁপা, বাট তোমার এই ক্রস সেকশন করলে সে একটা জায়গার বদলে মাল্টিপল জায়গায় সে হচ্ছে এটাকে হাইটটাকে ছেদ করছে, ইন্টারসেক্ট করছে, মাপা যায়। ওকে, তো সেই কারণে আমরা এখন এটাকে আর সারফেস বলতে পারছি না। বাট তুমি যদি এখন বলো যে স্যার আমি একটা টেনিস বলকে কেটে হাফ করেছি, তো সেই ক্ষেত্রে যেহেতু হাফ করেছো, তো অ্যাট সাম পয়েন্ট তুমি যদি এখন ক্রস সেকশন করো, তুমি যদি এখানে হাইট মাপো, ইউ হ্যাভ অনলি দিস হাইট, তুমি যদি এখানে হাইট মাপো, ইউ হ্যাভ অনলি দিস হাইট, তুমি যদি এখানে হাইট মাপো, ইউ হ্যাভ অনলি ওয়ান সিঙ্গেল পয়েন্ট। টেনিস বলকে যদি কেটে হাফ করে দাও, ওকে, একদম সমানভাবে হাফ করতে হবে কিন্তু, সেই ক্ষেত্রে তোমার শুধু একটা হাইট। ফর এক্সাম্পল তোমরা মাথায় যে টুপি পরো, টুপিও কিন্তু সারফেসের মতো, তাই না? তোমার মাথাকে ধরে সে বসাই দিচ্ছে, হ্যাঁ। তো এখন টুপিকে তুমি যদি ক্রস সেকশন করো, মাথার যে ক্যাপ যদি ক্রস সেকশন করো, মানে বেসবল ক্যাপের মতো যে ক্যাপ সেগুলো, তো সেই ক্ষেত্রে তোমার শুধু একটা পয়েন্টেই একটা হাইট পাচ্ছে, নির্দিষ্ট একটা পয়েন্টে একটা হাইট পাচ্ছে। সুই দিয়ে যদি ফুটা করো তাহলে ওটা শুধু একবারই সে কাপড়ের ভিতর দিয়ে যাচ্ছে, মাল্টিপল কাপড়ের ভিতর দিয়ে যাচ্ছে না, বা মাল্টিপল জায়গায় যাচ্ছে না। ওকে, so traditional GIS. So before the raster came in, before we started dealing with raster, so everything that we map was comprised of or made of point, line, and polygons. Should be one lines. So everything were made of point, lines, and polygons. And sometimes we, using these point, lines, and polygons, we also used to draw discrete objects, and still we do. We still do. We draw discrete objects. So what are these discrete objects? These are, for example, this road network maybe, okay, and then suitable plantation sites, okay. And also what we do using, so now we have point, line, and polygons, okay. The basic primitives are point, or the basic primitive is point. So based on these points, in geometry also we have studied that all the lines are made of multiple points. So we have, if I have connecting points, then finally I have lines, okay. And the polygons are nothing but a combination of multiple lines, or a line that closes at its starting point, so it creates a polygon. So the basic primitive is point. So we have point, lines, and polygons, however, to map out the things, to represent the reality in piece of paper or any other medium. And sometimes what we do is, by using point, lines, and polygons, we draw discrete objects, okay. And why do we draw that? Because we want to do mapping, and we want to make geoquery. Now, let me know if you do not understand my train of thoughts. Okay, আমি যেটা বলতে চাচ্ছি সেটা যদি বুঝতে না পারো তাহলে আমাকে বললো বলবা, ওকে? কারণ এই জিনিসটা দেখো খুবই সিরিয়ালি যাচ্ছে এবং ইটস ভেরি সিম্পল ইফ ইউ থিঙ্ক ফ্রম দিস পার্সপেক্টিভ। So traditionally in GIS, we have point, lines, and polygons to draw things, okay? What things? Discrete objects. Not continuous, but discrete objects, okay? And why do we do discrete objects? For mapping and making some queries. Okay, so the first purpose is mapping. We map out everything. Before the starting of traditional GIS in 1956 or 1856 or 1854. If I recall correctly, this is the 1850. This is the right year. So 1856, John Snow created the cholera outbreak map in London. So that was the beginning of this traditional GIS or historical GIS. Okay, that is the beginning of the GIS. And before that, in 1844, so John Snow actually took the idea from a Frenchman. Okay, so 1854, there was a French guy, a cartographer. He mapped out a cholera outbreak in France. Okay, maybe in Paris. So the idea was same, but the difference is in 1854, that is almost 12 years before John Snow, the French guy, he mapped out, I say mapped out, he only created mapping. Okay, he only mapped where are the choleras are, or where are the choleras outbreak. Okay, so that's just mapping. He didn't do any analysis. On the other hand, John Snow found out the correlation between the location of well, কুয়ার যে পানি, তখন তো আর এখনকার মতো ওয়াটার সাপ্লাই ছিল না, কুয়া থেকে লোকজন পানি নিত। So he found out the locations between the well and the distribution of the cholera. And using his study, then people were able to identify the contaminated well, which were contaminated by the virus of cholera. Okay, and those wells are then sealed. People didn't use it, and eventually people got better by using only the water from which are still not contaminated. Okay, so John Snow did the analysis, and the French guy, the Frenchman, he did the only mapping. So that's why this is only cartography. Okay, I forgot his name. I will let you know if I can find his name. And John Snow actually did GIS. Okay, so it's because he did analysis. And this is not analysis, this is just mapping. Okay, so in the first part, so this is mapping, and that's GeoQuery. Okay, so on the right hand side, we have similar examples. We have discrete mapping. We mapped out the discrete objects, for example, roads, and then boundary of different areas. So after getting some parameters or considering some factors, then what we did was we found out the suitable area for plantation. Okay, so we found out the suitable area for plantation sites. And how did you find out? Because we did GeoQuery. We made some query, we made some geographic analysis, and then we got these results, we got these boundaries. Okay, and all these things are possible. Things were possible because we had discrete objects. Okay, and we had discrete objects. How drawing these discrete objects were possible? Because we have point, lines, and polygons to draw them. Okay, so that's traditional GIS. So these point, lines, of polygons, all of them are vector data. So that's why a large part of GIS are involved in vector analysis or involved with vector data. And these vector data are considered as natural model. Why natural model? Because using vector data, you can draw anything, any entity of the world. For example, the house, then river path, or the bank of the river exactly as it is in reality, to the very much possible detail and to the very much possible precision. Okay, that can be done. That means how an object or how a phenomenon looks like in reality can be replicated exactly as it is in a scaled down form in GIS. So I say scaled down because in reality a river could be very big, very large. For example, Padma. So Padma is very large, right? So if you want to map out if you want to replicate its size and everything, if you want to preserve the size and shape and everything, then you need a large roll of paper which can fit a river. So what do? Instead, we take a small paper, we scale down the river. So that means by 1 inch, maybe we represent 1 kilometer in reality. Okay, but we preserve the details. Okay, we preserve the shape of the river. Okay, however, we scale down the size. So we do not preserve size, but we start preserving the shape. And the very much detail is possible after the invention of computer and all these graphics. The very much detail of the river is possible to preserve. And why I say very much detail is possible to preserve, because now if we go to QGIS, in QGIS, what we can do is, let me zoom in. So in GIS softwares, we are able to zoom in. So if we zoom in, we can see the very much detail. Let me quickly try to add one vector layer. So we have the map of US right in here. So if we zoom in, then we can see all this very much possible detail. And then if we find that, okay, it's not really straight line, it went a little bit, it has a little bend, or it has more points along the line, we can add them and we can alter them. Okay, so with the invention of computer and the graphics, now we can contain all the details that are possible. Okay, but in paper, it's not really possible. Why? Because if you have a paper which is A4 size, and for example, this is the A4 size, then you cannot draw to the very much possible detail of the state boundary or the county boundary in here, or in our previous example, the river bank. So however, since it is possible now, and the vector data can do that, we say it's a natural model, considered as natural models. And the coordinate space is continuous and not quantized as raster. And what do I mean by that? That means in vector, what it does, instead of having cells, it says that it's sort of very similar to the graph that you have drawn when you were studying at school. So in graph, you had your X and Y, and 1, 2, 3, 1, 2, 3, and you say that the first point is 1 and 1. So 1, 2, 3, 1, 2, and 3. So you said 1 and 1. So here you go, 1 and 1. So, and you say the next point is 2 and 1. Sorry, 3 and 1. So here is 3 and 1. Here is 1 and 1. And you say next point is 1 and 2. So 1 and 2. And you say the last point is 3 and 3. So here is 3 and 3. So you say now connect all this. So you see, I'm saying the first point is 1 and 1. So X is 1, Y is 1. So 1 and 1. Next point is X is 3, Y is 1, 3, 1. Then next point is X is 1, Y is 2. And finally, the fourth point is 3 and 3. So 3 and 3. X is 3, Y is 3. Okay. So why is it possible? Because at the background in raster, we have these cells, right? We have these cells. In vector, at the background, we have geographic coordinates, but these are not visible. We do not see that. We do not see them. Okay. For example, have a look at this point. Coordinate. Okay. If I move my mouse cursor, it changes. Do you see? Minus 110, 30, 39. It changes. Okay. If I go up, then y is changing. You see 35, 36, 37. So in this y is the latitude. So latitude is changing, or the y-axis is changing. If I go right, then x-axis is changing. Y-axis is fixed. It's 42 fixed. Okay, but that one x-axis became 94, 93, and so on. So that means wherever I put my mouse, let me put it here. You see 577, 379. So it's a continuous scale. Let me put it here. So minus 2,454, minus 1,271. So it's a continuously we have a coordinate plane or a coordinate space built in. So what do we do now? We match our values of our points. So 1, 1 will go in this location. Okay, 3, 1 will go at this position, and 1, 2 it matches this point of the coordinate space, and 3, 3 matches this point. So now what we can do is we can simply connect them. I connect them, and they became my polygon. Okay, so that's how vector works. Okay, so whenever you have a vector, you must think of that coordinate space. This is very important. If you have wrong coordinate space, then your things might go south. So things might go south means it's a phrase. Okay, so it might go wrong. For example, you have your data is collected in one coordinate system, so that is coordinate system number 1. Okay, so since it was collected using the coordinate system 1, so you said that this point is 1, 1, 3, 1, 1, 2, and 3, 3. Okay, so in reality, I mean, you went to the field and you collected these points, right? So in reality, let me draw this coordinate number 2 now. So coordinate number 2 is here. So 1, 1, 2, 3, 2, 3. So this is coordinate number 2. 1, 2, 3, 1, 2, 3. So 1, 1, 2, 1, 3, 1, 3, 3. Now in coordinate, using coordinate number 2, you have drawn the same region. I mean, you opened your QGIS or ArcGIS, and you define that your coordinate system is coordinate number 2, not 1. Okay, by accident or intentionally or unintentionally, you have identified that. But in reality, your coordinate system number is the data is actually collected in coordinate system 1. Okay, but in your software now you say that my coordinate system is 2. For example, here you say that my coordinate system is coordinate system 2. So the software will not realize that whether the data was collected in coordinate system 1 or 2. Okay, what it will do, if you force the software, it will do is it will match these values of these points. So 1, 1, 1, 1, 3, 1, 2, 1, and 3, 3. It will match and it will map it. But then when you start to compare with other objects, you start to realize that the feature that you have drawn, the area that you have drawn on your software is actually located in this part, in this location, and the size is actually smaller. And why did it happen? Because it happened because the coordinate system of 1 and 2 has a difference. So coordinate systems 1, 0, 0 starts at this point. Okay, but if we compare these two coordinate systems, then coordinate systems 2 might start from this point. So since coordinate systems 2 starts from this point, if we put them in the same plane, so it's 1, 1, it has 1, 2, 3, 1, 2, 3. So 1, 1, 3, 1, then 2, 1, and 3, 3. So now when you are projecting these data collected in coordinate system 1 in coordinate system 2, it's now mapping in this form, in this shape. Let me draw in this way. So that's your region now, but in reality it's actually located in this location. So that's how you have to be very careful. You have to be very careful of which coordinate system your data were collected in, and which coordinate system that you are projecting when you are importing your data in the software. Okay, and just like as I said earlier, the primitive point is fundamental primitive is the point, because based on the point everything is built on. Okay, so does anyone have any question? No question? All right, so that means we are end of our class. Thank you and good luck for the class test. Bye. Turn off.